Once the oil and gas is in production, there are still many tasks for the teams of production and reservoir engineers to perform. With all of the variables involved in producing oil and gas, it is a tribute to our modern-day engineering that we can do it so well. Now, let's look at some long-term problems that can occur in production. Pressures, temperatures, and water levels in the reservoir must be monitored and controlled. Corrosive substances like H2S gas, CO2 gas, and water in the oil can destroy the steel pipe, eventually causing the equipment to fail. In addition, the production of scales or hard rock deposits that build up on the inside of the pipes and valves, and hydrites, or a slurry of frozen water and oil at the surface, can also cause problems by restricting the flow of the hydrocarbons. Over time, therefore, a producing oil or gas well will have to be reconditioned or repaired if optimal production is to continue. Known as a workover, a recompletion, a reconditioning, or a remedial, the purpose of a workover is to re-enter the well to repair it. Smaller than the original drilling rig, a workover rig can be brought to an onshore site by truck, to a protected water site on mobile jackup barges, or to a deeper water offshore location on a platform-based unit mounted on skids. Workover units come in various types. Here we will discuss 4 workover rig types. The slickline wireline units. These workover units consist of a single strand wire that is used for routine maintenance of gas lift valves, chokes, sliding sleeves, and for cutting paraffin accumulation in the tubing. Here is an illustration of a slick line that is run during tubing under pressure using a lubricator. This procedure is used to measure the tubing diameters to help better gauge corrosion or deposits. Electrical conducting wireline units. As this illustration shows, this multi-strand electrical conducting wire is used for logging, perforating, and setting plugs and packers. It is run both through tubing, under pressure, and through casing when the well is killed or taken off production. This procedure is used to run production logs, which can help determine fluid flow rates and gauge the current effectiveness of perforations. Coiled tubing units. As you can see here, these units are small diameter, 3 1/4 inch to 1 1/2 inch continuous tubing with no joints. Spooled off a reel into the hole, they can run either through tubing or through casing. Coiled tubing units can be used to clean out sand or to place cement or remove scaly deposits. They can also be especially useful for working horizontal holes. Pulling units. These mobile onshore units using 2-inch or 2 1/2 inch outside diameter jointed tubing operate as a work string. These pulling units are multi-purpose machines because they can be used for routine pulling of rods and tubing as well as for major workovers. Notice that the drawworks here is smaller than those used on drilling rigs. A rotary table and a reverse circulating mud system can also be attached for drilling out plugs, junk, or for deepening the hole. These pulling units work with the tree removed, so flowing wells have to be killed, which means that production is stopped. The last one we mention here is not a workover rig, a conventional drilling rig. The drilling rig that was first used to drill the original holes on deep water platforms is left in place to later act as a workover rig. Choosing the right unit is important because there are many types of workovers. Let me explain in a little more detail the steps involved in doing a typical workover using a pulling unit to reperforate a new zone above a depleted one. As you've seen in other chapters, there may be more than one pay zone in the reservoir. Often, the bottom zone is completed initially and produced to depletion. When this occurs, the well is then worked over to plug off the old zone and complete a new one in the upper zone. Let me walk you through the process in an onshore well. First, load fluid is pumped down the tubing to kill the well. Second, a pulling unit is moved on location where the tree is removed and replaced with a BOP. Then, the tubing and packers are pulled. Third, a packer, called a cement retainer, is run on an electric wire line and sets the retainer above the old zone. Next, a tubing work string and latch are run into the retainer, followed by the pumping of cement down the tubing into the pay zone until it pressures up or won't take any more cement into the perforations. This is called squeeze cementing. After that, the tubing is unlatched from the retainer and a flapper in the retainer swings closed to prevent cement from flowing back up. Then water is pumped down the annulus and up the tubing in what is known as reverse circulation to clean out the cement left in the tubing. After that, the tubing is pulled from the hole and a perforating gun on a wire line is sent down to perforate the upper zone. Finally, the upper zone is fractured, acidized, or gravel packed before the tubing and packers are run back down. The Christmas tree is reinstalled and the well is brought back to production. To unload the kill fluid, it might be necessary to pump liquid nitrogen down a string of coiled tubing run inside the production tubing. Other types of workovers might include re-stimulation. Here, the original pay zone may need to be re-acidized or refractured. Deepening to a new zone. In this workover, the existing perforations are squeezed off and the hole is drilled deeper to a new zone. Because it is deeper, a casing liner has to be run, cemented, and completed. As you can see from our first example of a workover, it is preferable and much easier to deplete the deepest zone first. Repairing casing leaks. When casing leaks occur, it may be necessary to set a bridge plug below the leak and a packer on a tubing above the leak. Cement is then squeezed between the bridge and the packer to seal it, like a patch. Repairing casing leaks can also be fixed by setting a scab liner over the leak. A scab liner is a short piece of smaller diameter casing with packers on both ends or a packer that expands outward to seal the leak. Repairing faulty well equipment. Here, worn-out downhole equipment is replaced, such as leaking tubing, broken sucker rods, malfunctioning gas lift valves, or leaking packers. As you can see, maintenance operations are vital in maximizing oil field production. They require good engineering over the life of the well and the field. In Chapter 9, we explained and illustrated the equipment and procedures involved in field appraisal and development that helped you get answers to the questions raised at the start of this lecture. Where needed, we highlighted the similarities and differences between onshore and offshore field development. Starting with onshore, we described the equipment, the production tests, and procedures used for a field appraisal and emphasized some factors that must be present if the exploration field was to become a production field. Next, we described the equipment and procedures needed for site development of surface facilities that needed to be in place as the field was brought into production. We discussed those facilities that needed to be on site and some safety and economic concerns that could affect the placement of these facilities. We concluded by looking at wells that needed to be reworked or refitted due to falling rates of production, usually after a well has been in production for some time. Illustrating workover units, we then explained a typical procedure where a pulling unit was utilized to abandon an oil pay zone and reperforate a new pay zone higher in the structure. Overall, in this chapter, we explored the various methods used to maximize field development. Good engineering in field appraisal and development starts us off in the right direction that will ensure that our field will produce for a reasonable amount of time. Most likely utilizing primary drives in the initial stages of production, our field can produce to our calculations, but there may not be enough lift to ensure that the hydrocarbons in the reservoir are optimally depleted. Even with good technology and engineering in appraising the field and producing it, it may be necessary for us to use more interventions. In Chapter 10, we will discuss artificial lift and its role in optimally depleting the hydrocarbons from a field.